All right, so this is a little bit of review. This is what a discrete random variable, how we show the probability distribution of a discrete random variable. So what do we do with a continuous random variable? We've worked with these before. A continuous random variable, we simply describe the probability distribution by looking at the density curve. If you recall, the most common density curve we studied was the normal curve, but we also studied a uniform curve. I think on one test I even gave you one where you maybe had something that was uniform and for bid and then something like that. I don't know. But what they all have in common is the area under all of these curves is 1 unit. One area is 1. And probabilities are assigned to intervals as areas under the curve. So if you find the area underneath the curve, that's the probability that if you randomly selected a data point in that distribution, it would be between those two numbers. Okay? So, like I said, this is nothing new. Just revisiting it and thinking about it from a different perspective. Well, not even a different perspective, same perspective. Reviewing it. Let x equal a random number between 0 and 1 inclusive. Where every number is equally likely. Well, if everyone's number is equally likely, then we simply have a uniform density curve. This is kind of the one time we don't label the y-axis. It's called the probability density. It's not really a probability. It's a probability. Well, whatever. Don't worry about labeling the y-axis. So this is a probability distribution. I can't make a table of values because I can't list all the values because there's an infinite number of them. And even if I were to list one of them, 0, 0, 0, 0, 0, the probability of that one value occurring is 0. Because there's infinitely many, the probability of any one of them is nil. So instead, we just draw the graph. Find the probability that, so let's find the height of this. The width is 1. The area underneath it is 1. So 1, this is a rectangle, of course. So 1 times h is equal to 1, so h is equal to 1. This is equal to 1. Find the probability that x is between 0.3 and 0.7. That's just the area under the curve between 0.3 and 0.7. That is a rectangle with a width of 0.4 and a height of 1. So that would be 1 times 0.4, or 40%. That's inclusive of 0.3 to 0.7. If we do exclusive 0.3 to 0.7, it's the exact same thing because it doesn't matter if you include the endpoints or not. The probability of getting an exact value is 0. So same answer. More commonly, we work with a normal distribution. Weights of 3-year-old females closely follows a normal curve with a mean of 30.7 and a standard deviation of 3.6. Let x equal the weight of a randomly selected 3-year-old male. I'll just point out to you that the only thing that's new here is that we're calling the weight of a randomly selected female x, a random variable x. Other than that, it's the same thing we've done before. Is x continuous or discrete? Well, we are using a normal distribution, so in this case, x is continuous. Why? Because we are using we or they, somebody, are using a normal model. If we're using a normal model, that is a continuous model. So we are looking at this as a continuous variable. Now we could record weights discretely, and normally we do, but if we're going to model it, we're going to use a continuous curve in this case. Find the probability that a randomly selected 3-year-old weighs at least 30 pounds. So let's review what we need to show for our work on this. We need to put down the word normal or draw a normal curve. That gets me credit for normal. I need to explicitly state the mean. just recording it there. Explicitly state the standard deviation. And then I want to calculate the probability that my random variable x weighs at least 30 pounds. So that's that they weigh 30 pounds or more. So that would be 30 pounds or more. The last piece of information we got to put on there is the cutoff and the area we're trying to find. Now we use our calculator, use a shortcut, make it easy on yourself. Menu, statistics, distributions. Just to review, normal PDF you don't ever use. Normal CDF you use if you have the cutoffs and you want the area. Inverse normal you use if you have the area and you want the cutoffs. 30 to infinity. 30.6 or 7? 7 and 3.6. So in the book, they're going to do z-scores and all that stuff. You can do it if you want, but just use the calculator to its full potential. 0.577. 0.577. So there's a 58% chance that you're going to get a girl that weighs over 30 pounds. Find the probability that weighs between 25 and 30. This is just being repetitive. I'm sorry. 25 and 35. You just change the cutoffs. So who cares? Find the probability that x is less than some constant k. If the probability that x is less than some constant k is 80%, then find the value of k. Now I don't need to draw a new curve necessarily. I have credit for normal. I have credit for the mean and standard deviation in this problem already. But I do want to just visualize it and get the cutoffs right. The probability that x is less than k is 80%. So if k is some cutoff, there's 80% chance that it's less than that and a 20% chance it's more. They want me to find the k value. I have the area. I want the value. Now if you want, you can find the z-score, but I'm just going to use the calculator to get the value. Now I have the area. I want the cutoff. That's inverse normal. Which area am I going to put in? This function always takes the left area. So I got to put in the 0.8. Hit enter. You get the z-score. And you could convert that if you want. I don't want. Make it easy. 30.7, 3.6, 33.7 pounds about. K is approximately 33.7 pounds. Okay. All right, that concludes section 6.1. Next video we'll have 6.2.